So all right, this last chapter that we're doing is about matrices. So a matrix, hi, come on in. This last chapter is about matrices. The singular of that is matrix. So it's a matrix we typically name with a capital letter. So like this matrix, I'm going to name with a capital letter I. And what a matrix is it's like a rectangular array of information. Now, typically, we use like the brackets to write our array. And the things in the array, so let's say this is like, I have 2 rows of information and 4 columns of information. So we'd say that this is a 2 by 4 matrix. Because we have 1, 2 rows, and then 1, 2, 3, 4 columns. We always write the rows first and the columns second. And that 2 by 4 we call the dimension for the matrix. So far, so good. So the information contained in the matrix for us is just going to be like a number or a variable. Could be other things, but that's beyond the scope of what we're doing in this class. So it'll just be like a number or a variable or like a variable expression. Each of these positions inside our matrix has a different name. So I would name this first spot with a lowercase a, since our matrix is named with the uppercase A. And since it's in the first row and first column, I would name it A11. The next spot here, because it's in the second row, or the first row in the second column, I would name A12. This one over here, I would name A13, A14. Everybody's okay with that? Or that subscript is describing what row and what column that entry is appearing. So this one would be like A21. Then we'd have A22, A23, and then A24. Everybody's okay with that idea? Fairly simple, but it's important that we understand these naming conventions because they'll become important later on. So there is a special kind of matrix that becomes important a little bit later on called a square matrix. What do you suppose the dimension of a square matrix is? Yeah, something like 4 by 4, 3 by 3, or in general we'd say n by n, right? So any one where I have the same number of rows and columns. So just as an example, let's say we have this matrix here that I'm calling A. What is the dimension of this matrix? 3 by 2. Yep. Because I have 1, 2, 3 rows. And I have 1, 2 columns. what is the entry A22 going to be? 9. Good job. And say, like, what is A31? 6. Great. Does everybody feel pretty comfortable with what we've done so far? Not much, right? Okay. What we'll define next is equal matrices. And we say that matrix A is equal to matrix B if and only if two things. The first is the dimensions have to be the same. And the second is every entry in A has to equal the corresponding entry in B. Okay, so let's take a look at this example. Here it says to solve for x and y. The key for this problem is noticing that these two matrices are equal. Since the matrices are equal, I know that the corresponding elements are equal. So I can say that x minus 3 is equal to -1. And then similarly, I can say that 3y minus 1 is equal to 5. And then it's super easy, right? No biggie, right? Just that important observation that the two matrices are equal means I can set the corresponding elements equal to each other. Okay. So now we'll talk about matrix addition. So if I want to add two matrices together, we say A plus B is defined if and only if the dimensions of the two matrices are equal. And how do we do matrix addition? Well, if A plus B is equal to C, then Cij is equal to Aij plus Bij. So all I'm going to do is add the two corresponding entries in A and B and put them in the same spot in C. So it's going to work exactly like you would hope. Let's do a quick example to illustrate this. So let's say we want to add these two matrices together. First thing I should check is to make sure that they have the same dimension. What's the dimension on the first matrix? 3 by 2. And the dimension on the second matrix is 3 by 2. So we can definitely add them together. If they were not the same dimension, you can just write undefined, right? If you have two matrices that aren't the same dimension, you can't add them together. So what does this mean? Well, the first entry is just going to be the sum of the first two entries. And we can just go on doing this. Again, you could probably do these arithmetics in your head. I'm writing them out just because they're notes, right? And it's sometimes helpful to have like a little bit more information there. Everybody feel okay there? Matrix subtraction, exactly the same, right? You're just subtracting instead of adding, but same rules, works the same way. Any questions so far? Okay. Now, for matrices, there's actually two kinds of multiplication. The first kind we're going to talk about is scalar multiplication. So scalar multiplication is a real number times a matrix. And we can always do scalar multiplication. So scalar multiplication is always defined. That's great. And if we say KAB is, or K times A is equal to B, then Bij is going to equal K times Aij. So all we're doing is multiplying each entry in our matrix by that scalar K, and that'll be my new matrix. So it's kind of like a big distributive property. Let's do a quick example, make sure that we got it. So there's my scalar here is 3, and my matrix is all of this stuff, right? Everybody see the real number times a matrix? Sometimes we call that real number a scalar. So all I'm going to do is multiply each entry in my matrix by that number 3. And again, that's probably something you could do in your head, but since they're notes, I went ahead and wrote in that intermediate step just so that there's no confusion about what happened. Any questions about scalar multiplication? Again, pretty easy, right? This is working just the way we'd expect. So far, this is not much more than like a big arithmetic problem, right? Nothing tricky. The next piece is matrix multiplication. So this is going to be between two matrices. Okay, so matrix multiplication is a little bit more complicated. than any of these other operations. First of all, if the two matrices are the dimension, or for the to be able to do matrix multiplication, the dimension has to be in a specific format. So if this is matrix A is dimension n by m, matrix B would have to have a dimension m by p, where the number of columns in matrix A has to equal the number of columns on matrix B. Let's write it this way. So if that's the case, my resulting matrix is going to have dimension n by p. So this is kind of weird already, right? The analogy I like to make for students is that matrix multiplication is a little bit like falling in love. Just because two people look different on the outside, they're kind of the same on the inside. And when they fall in love, they can have a child, and that child looks a little bit like one parent and a little bit like the other parent. Aww. Everybody so far so good? So we've just talked about the dimension piece of it. We haven't talked at all about like how we actually do this multiplication. And this is going to be a little bit tricky. All right, so let me make sure I get this right. So entry Cij is going to be A1 1 times, nope, it's going to be AI1 times B1J plus AI2 times B2J all the way out to AIM times B yeah, so that MJ. Sorry, it gets a little confusing with the subscripts there for me. Let's do a specific example, and it's really not as bad as it looks here. Visually, it's a little bit easier to kind of remember what's going on, and I'll show that to you guys here when we do our actual numeric example. I would not try to memorize this definition. It's much easier to kind of attack this visually, which I'm about ready to show you. Okay? Okay. So here's my first example. So first thing we need to check is the dimensions on our matrix. Our matrices, excuse me. What's the dimension of the first matrix here? 2 by 2. And the dimension of the second matrix is 2 by 3. And since the columns in the first matrix and the rows on the second matrix are equal, we can indeed do this matrix multiplication. So my resulting matrix is going to be a 2 by 3. So what I'm going to do is I'm going to start by writing out a picture of my 2 by 3 matrix. And I'm going to put a space for each entry that I'm going to put, or I'm going to compute anyways. So this is like entry 1, 1, entry 1, 2, entry 1, 3. And this would be entry, 2, 1, 2, 2, and 2, 3. Everybody so far so good? So I like to do it this way because the subscript is telling me which row I need from the matrix on the right and which column I need from the matrix on the left. So I'm just going to be multiplying the corresponding entries and then adding them together. So the first entry times the first entry, the second entry times the second entry, and add them together. So visually, this is much easier to kind of understand and remember than the previous, formulas were. All right. Let's look at the next one. So here, again, we're using row 1, but this time we're using column 2. So we'd have 1 times 1 plus 3 times negative 6. Is that okay? Uh-oh. And my last one for this row, I need row 1, but this time I need column 3. So I'll do 1 times 3 plus 3 times 5. You guys feel okay with what we're doing so far? You kind of getting the hang of the pattern here? Again, visually, I think this is rather intuitive once you've seen it and see how, like, oh, if I just name the entries, like, tells me exactly what I need to be multiplying together based on the names, and it's not too bad. If I think about it as like a formula, it's like, ooh, buddy, that's a confusing looking formula. So let's just go ahead and write in the rest of these. Oh boy. That's fine. All right. So here we're using row 2 with column 1. So we have 2 times negative 3 plus 4 times 2. And then we're going to do row 2 times column 2. So 2 times 1 plus 4 times negative 6. And then lastly, row 2 times column 3. So we have 2 times 3 plus 4 times 5. So simplifying these down, negative 3 plus 6 is 3. 1 plus negative 18 is negative 17. 3 plus 15 is 18. Negative 6 plus positive 8 is 2. 2 plus negative 24 is negative 22. And 6 plus 20 is 26. What's up? Yeah. And this is, again, like once you've got the pattern, it's not really that difficult. It can be time consuming maybe to, like, if the matrices are big, but we went really slow and I wrote a lot of stuff down that maybe isn't always that necessary to write down. But again, for you guys that are just kind of doing this the first time, it's probably helpful to kind of write it all out like I've done here until you get the hang of it. Let's do this example here. So again, matrix multiplication question. First thing we need to do is check the dimensions. Very good. What's the dimension on our first matrix? 2 by 1. And on the second matrix, 1 by 2. So we can multiply these together. What size will my resulting matrix be? 2 by 2. So I'm going to just write the names of my entries under the spot I've put in for each entry. Okay. To get C11, what do I have to do? First row by first column, right? Cool with that? And then we'll do the next spot will be first row and second column. And then first row and second row and first column. And then lastly would be second row and second column. And we're done. So sometimes it's really easy still, right? Just kind of depends on how much stuffs are in there. Not too, this one was pretty easy though, right? All right. So another special matrix is called the identity matrix. Maybe we should say, I should say, be specific, multiplicative identity matrix. So when we multiplied real numbers together, like way back in elementary school, what was the multiplicative identity for real numbers? It's the number that you can multiply with that just gives you the same number back every time. 1, right? So 1 times a number is itself. What's that matrix going to look like for a multiplicative identity? Well, they have to be squared, right? The multiplicative identity is going to be a square matrix. So I'm going to write n by n down there. So for, well, let's just do it simpler than that. So 1 by 1, sure, is that. For a 2 by 2, it's going to look like that. For a 3 by 3, looks like that. Anybody detected the pattern yet? So the pattern here is that we have 1s down the main diagonal and 0s everywhere else. So 1s there, and then 0s everywhere else. Oops, forgot to close that up. Everybody cool with that? So next operation we want to talk about is the determinant. And what this does is it takes a matrix and turns it into a real number or a scalar. For the determinant to work, that matrix has to be a square matrix. If you're not using a square matrix, you cannot take the determinant. The symbol that we use for the determinant are vertical bars. Or sometimes we'll just write DET in front of it, short for determinant. Or sometimes we'll write our matrix, but we'll use vertical bars there instead of the brackets. So any one of those three symbols, or three ways of writing it, means the determinant of our matrix. Everybody's okay with that? The thing I want to really caution you about is this first notation and this third notation. So there is no such thing as an absolute value when dealing with matrices. So we need to make sure you're critically important that you remember that the vertical bars around a matrix mean the determinant. The vertical bars around a number is absolute value. Okay? So there's no such thing as the absolute value of a matrix. Not a thing. We're talking about determinants. Okay. So let's talk about how you do that. We're going to do two examples. So I'm only going to expect that you're able to do by hand a 2x2 determinant or a 3x3 determinant. Okay, so this is a 2x2. The way we do that is we take why is my pen stop working? There we go. Okay. We're going to take the product of the first diagonal, of the main diagonal, and then subtract the product of the other diagonal. That's it. Two by two, very easy, right? Simple formula, easy to remember, it's very visual. Any questions on that? Okay. For a 3x3, this becomes a little bit more complicated, but it's still not bad. It's very visual. So I'm not going to give you a formula for how to do this. I'm just going to kind of show you visually what to do. So the first thing we'd want to do is we want to recopy the first two columns. And we're going to always write those first two columns on the right side of our matrix. Then we're going to add up the product of the three down diagonals. So 3 times 1 times 2 plus -1 times 7 times -4 plus 5 times 2 times 7. Yeah, come on. It's okay there. And then we're going to subtract the product of the three up diagonals. So -4 times 1 times 5 minus 7 times 7 times 3 minus 2 times 2 times -1. Now, I wrote that on 2 lines just because it wasn't going to fit on 1 line without everything getting really small. But that's all just like 1 line of calculation, right? Okay, so 3 times 1 times 2 is 6. Negative 1 times 7 times negative 4 is 28. 5 times 2 times 7 is 70. Negative 4 times 1 times 5 is negative 20. 7 times 7 times 3 is 147. And 2 times 2 times negative 1 is negative 4. So let's see, that's 78 and 104 and 124 and 128 minus 147 is negative 19. Again, a lot of numbers to crunch, but the actual formula here, the process, very visual, not too bad to remember, right? It's the 3 down diagonals added together, and then minus the 3 up diagonals. Okay. If you're a visual person, this should be relatively easy to remember. With a little bit of practice, should stick pretty good. The last content piece I want to talk about is multiplicative inverses. So let's go back again to elementary school. Examples of multiplicative inverses would be 2 numbers that multiply to give you the multiplicative identity, which was 1. So for example, 2 times 1/2 gives us 1. So 2 and 1/2 are inverses. Does that sound familiar? Maybe you didn't use the vocab, but like, you know, a number and its reciprocal. When you multiply them together, give you 1. Everybody's okay there? So the same is true for matrix multiplicative inverses. The only one the only situation I'm going to expect that you're able to do by hand is for a 2 by 2 matrix. So the symbol that we're going to use for the multiplicative inverse of A is A with the -1 exponent, just like, because we know the -1 exponent means like a reciprocal. It kind of is supposed to cue us that we're talking about a multiplicative inverse, just like we did for real numbers. So our formula is going to be 1 over the determinant of A times the matrix D, -B, -C, A. Notice that this matrix on the right is just a version of our original matrix. We notice we swapped the entries along the main diagonal and then negated the entries on the other diagonal. Let's do a numeric example just to kind of demonstrate. All right. So we have 1 over the determinant of A. So that's going to be -6 times -7 minus 5 times 8. Everybody's okay? Now we need to write our our new matrix here. So remember, we swap the entries along the main diagonal, and then we negate the other entries. When I say negate, I really mean switch the sign, right? So if this was like a -8, it would become +8. Everybody's okay with that? When I say negate, it means if it was negative, it would then turn positive, right? Okay. All right, so -6 times -7 is 42. 5 times 8 is 48. So I have 1 over 2 times this matrix. So that's scalar multiplication now, right? Notice that the fractions I could reduce, I reduced, and the ones that I couldn't, I just left as fractions. Everybody okay with this? So it's basically just a formula, right, that you're following? As a separate question, does a matrix multiplicative inverse always exist for a 2x2 matrix? Is this always possible to do? Some people say yes because they can't see a reason why it wouldn't. But Landon is going to psychoanalyze this and say that, like, you wouldn't be asking us this question if the answer was yes. So I'm going to say no. No is the correct answer. Let's go back and look at the formula here for a moment. Where could this fail? Where could we get in trouble? What could happen so that the inverse wouldn't exist? Nope. The potential problem area is here. What value could that determinant have to get us into trouble? 0, right? So if our matrix has a 0 determinant, its inverse does not exist. Okay? So that can happen, just as a heads up. Important point to make, right? Because certainly you'll see that in the homework or elsewhere where something has a 0 determinant and there is no inverse for that, and that's okay. Doesn't mean there's anything wrong, doesn't mean that you did anything wrong, it just that this can happen. All right. One of the lovely pieces of matrix operations is that all of these things I've shown you, we can do on our calculator. So if you have your calculator with you and you'd like to follow along, I invite you to take that out. If you're a sit and listen and watch kind of dude, you can certainly just chill and sit and watch. But I think it helps to kind of go through the steps on your own calculator so you get some practice pushing the buttons. You know, but at 16, 17, 18 years old, I trust that you kind of know yourself well enough to know what works for you. All right, primarily what we're going to be using is the matrix menu. So you can access the matrix menu by pressing the second button and then the x to the -1 button that's like right there below it. That'll open up the matrix menu. You guys, if this is the first time you've ever been in here, you probably won't have anything written in this column here. It'll probably just be all blank because you've Haven't used it before, and that's okay. To type a matrix into your calculator, we're going to move over to the Edit tab, and we'll select a matrix, select matrix A, and then you can type type in the values for matrix A. The values we're going to use for our practice problem are 2, -5, 6, and -4. Let's just do that. So notice that you have to type in the dimension of your matrix to start. You have to say 2 by 2. Once you've type those 2 and 2 in, it'll give you the spots to type the rest of the things in. You just press enter each time you type a number, and the calculator will automatically toggle your cursor to the next spot. If you need to go back and retype something, you can just use your arrows to move back to the spot you want to get to. Type something in and then press enter, and it'll update whatever was there. Okay. Let's go press second and the matrix button again. Move back over to the Edit tab, and this time select matrix B. And we're going to make matrix B 1, -3, +3, and -5. Yep, I'm going to write them down here on my paper as well because I know it can be hard to see. Okay. There's that. So I'm going to exit out of here. Let's say I wanted to add these matrices A and B, right? So if I want to do that, I'm going to go back to the matrix menu. From the Names tab, I'm going to select matrix A. I'm going to type the plus sign just on my normal keypad. Go back to the matrix menu and select matrix B, and then press enter. Cool. Let's say I wanted to do 5 times matrix A, like a scalar multiplication problem. So I'm just going to type 5 times, and then I'll go back to my matrix menu, select matrix A, press enter. No big deal, right? Next, I'm going to go back to my matrix menu. Let's say we want to do matrix A times B. So I'll just do A, type in the time symbol, and then B. Press enter. No big deal so far. What if I want to do B times A? What are you guys expecting to get here if you do B times A? The same thing, but what do you notice? It's not. This is not a mistake. Nothing has happened wrong on your calculator. Matrix multiplication is not commutative. That means that A times B does not necessarily going to equal B times A. So, when you're doing your work, you have to make sure that you're not swapping the order of your matrices all willy-nilly like you can with real numbers. The order in which you're multiplying matrices has to be the same order that's on your sheet of paper. Okay with that? Okay. Your calculator can do determinants also. To get to the determinant command, we're going to press second and then the matrix button. We're going to move over to the Math tab, and notice the first option under the Math tab is DET. So I'll do the determinant of, say, matrix A. That gives me 22. Cool with that? Since this determinant is non-zero, I know I can find an inverse for matrix A. To do that, I'm going to go back to the matrix menu, select matrix A, and then I'm going to type in the -1 button. So I'm going to put a -1 exponent on it, and then press enter. And I got this pretty gross looking set of fractions here, But what's nice about this is if I press the math button and select the fraction option, the calculator will go and write that as fractions for me, which is way nicer looking than those big kooky decimals. And regardless of the size of these matrices, whether you're talking about like a 3 by 3 or a 4 by 4 or a 5 by 5, the calculator can handle taking the determinants and inverses of these things. So you do not need to do those kind of things by hand, right? So on an exam, I would give you things that you can do by hand, and I would expect you to do them by hand, showing some intermediate work. Now, you'd be silly not to start by typing the problem into your calculator and know what the right answer is so you can catch any mistakes you're making along the way. But I would expect that you're able to kind of do things by hand and show the intermediate step of like, okay, this is how I'm getting the entries. I'm multiplying this thing times this thing, or I'm adding, this times this plus this times this, or, to get the determinant, I multiply all these things together and add this stuff, like you're showing me what you would do by hand. Now you can use your calculator to get the actual answer, but like you should show the setup. Landon.
How many lessons are there in the exam? Just this one?
Right, yeah, just the rest of this week is all we're doing. We're just this will finish this chapter B. So we have, 2 more sections after this. The last one's kind of the difficult one.
So like, we could probably expect like a question per day, right? You said there's 3 questions.
Yeah, that's probably not an unfair, really I would say almost that section 3 is just so you can do the stuff in section 4. Is almost the reason why we're doing section 3. So it's kind of, I'm going to do an abbreviated version of it because I just want to do enough so that I can do this stuff in section 4. But we're kind of taking a, like abbreviated trip through this. Like we could do a lot more here, but we're just kind of doing a little bit of basics. Is that cool? Yeah.